Hi, this is question 6 from the AQA Core for January 2013 exam paper. For the first part of this video, I'd like you to see if you can have a try at the question. So if you'd like to pause the video now and give it a go. Okay, well done if you managed to have a go at the question. I'm now going to go over a hint as to how you can go about answering the question. We're given the points A, B and C, and we're told their coordinates. We first of all want to show the vector AC is given by this here. So I need to know the direction in which you would go to get from this coordinate to this coordinate here, AC. So you would want to do the position vector of this and subtract the position vector of this one here. Part 2 says show that the acute angle ACB is given by the inverse cosine of this over here. So for this part of the question, you want to use the fact that AB over the magnitude of A times by the magnitude of B is equal to cos theta. Now what you need to be careful about is the direction in which the vectors are facing. So if we want ACB, then we need to find the vectors that are either both pointing towards C or pointing away from C to give us our angle. Okay, part B says find a vector equation of the line AC. So we want to write our line in the form R is equal to A plus lambda B, where A is a position vector that lies on the line and B is a direction of the line, and you will have already found the direction of the line and you should already know a point that lies on the line as well. So we should just be able to stick something straight into this. Okay, part C says the point D has coordinates 6, negative 1p, and we're given that the lines AC and BD intersect each other. So we first of all need to write down a direction vector BD using this here, and that will be in terms of P. We also know a point that the line D goes through, which is this. So we can also write our line BD in this form here, where we've got it in the form R is equal to A plus lambda B, but we might want to use a different letter for our parameter here. We can then, because we know that they intersect each other, we can then make the equation of the line AC and the equation of the line BD equal to each other, and we should be able to then go on and find what P is. Part 2 says show that the ABCD is a rhombus, let's take the length of each of its sides. Now the property of a rhombus that we want to use for this is the fact that a rhombus has got 4 equal sides. So if we can prove that that each of the position vectors AB, AC, BC and AD all have the same length, so they have the same magnitude, then we will be able to show that it is in fact a rhombus. Okay, so those are my hints. I'd now like you to pause the video and see if you can have a go at the questions yourself. Okay, well done if you've managed to have a go at that. I'm now going to go through the answers to the question. Just going to create a little bit more room for myself to work in over here, and I'll stick this up here for the time being. Right, okay, so starting with A part 1. Okay, so we want to show that the vector AC is given by this, so I want to do the position vector C, take away the position vector A, to show this. So I can say that AC is going to be equal to, and the position vector C is like the origin to this coordinate C, so that's going to be 8, -4, -6. Take away, and the position vector of A, which is going to be 3, 1, -6. Okay, so that's going to be 8 subtract 3 is 5, and that's going to be -5, and that's going to be 0, and that's actually equal to 5 lots of 1, -1, 0, as we're required to find over here. So n is 5. Okay, part 2. We want to show that the acute angle ACB is given by this here. So I said earlier that we want to use this formula here. So that's A dot B. Okay, so we want to find the dot product of A and B and divide it by the magnitude of A times by the magnitude of B. So before I start this, I first of all need to know what the vector AB is. Sorry, I want to know ACCB. Sorry, I want to know what the vector BC is. I beg your pardon. Okay, so BC is going to be C take away B. So position vector C take away position vector B. So that's going to be 8, -4, -6. Take away 5, -2, 0. And that's going to be 3, -2, and -6. Okay, so now I want to do the dot product of these two, and then divide by the magnitude of this one times by the magnitude of this one. So and that's going to tell me what cos theta is. So cos theta is going to be equal to, and if I do the dot product of these, I'm going to have, well, that 5 is just an integer that I'm going to times it all by. So I'm going to have 5 times, and 1 times 3 is 3, -1 times -2 is 2, so plus 2, and 0 times -6 is just 0. So that's that. And I want to divide that by the magnitude of this one here. So the magnitude of this is √2. So this is going to be 5√2. And the magnitude of this here is going to be root, and we're going to have 9 plus 4, which is 13, plus 36, which is 49. So it's going to be √49, and in fact √49 is 7. So that's going to be 5 times 5, which is 25, over 5√2 times 7, which is 35√2. Simplifying that, 5 over 7√2. And there you go. Now it says over here that we want this in the form 5√2 over 14, so they've rationalized the denominator over here. So I'm just going to multiply the top and the bottom by √2 to rationalize the denominator. So that's going to be 5√2 on the top, and √2 times by √2 gives me 2, times that by 7 gives me 14. So I'm going to have 5√2 over 14. Yeah, just to clarify, I've multiplied the top and the bottom by √2 to rationalize the denominator, and I've got that there. So that means that theta, or the angle in between, so the acute angle ACB, is going to be the inverse cos of 5√2 over 14. Okay, someone at the door. I'll be right back. Okay, right, so I've just moved some of the work in over here. We're now going to work on part B, and in part B we want to find a vector equation of the line AC. Now, I already know the direction in which AC is going in, and I also know that it passes through, and I can use either of these points, A or C, but it passes through both of those points, so I can write it in this form here, where a general point on the line is going to be equal to a position vector plus any multiple of the direction vector. So so for part B, I can say that R is going to be equal to, and I choose any position vector A that I want. I'm going to go with this one here, so 3, 1, negative 6 plus lambda times by the direction vector. So the direction vector here, I could use 5, negative 5, 0, but I'm going to use a simplified version of it. It's going in the direction 1, negative 1, 0, so we can use that one. Okay, right, so and that's part B. That's a vector of equation of the line AC. Okay, part C. This time we are given that point D has coordinates 6, negative 1p, and we're also given the lines AC and BD intersect each other. So we want to use that information to find the value of P. Now, in order to find a point of intersection, which I'm guessing I need to do to work out what the value of P is going to be, I need to have an equation of the line BD as well. So I've already got AC, which is this one here. So I also want to have the vector, sorry, an equation of the line for the vector BD. Okay, so I first of all need to find the direction in which BD is going in. So BD, and that's going to be the position vector of D, which is this one here. So 6, negative 1p. Take away the position vector of B, which is this up here. So that's the coordinates, so the position vector is going to be 5, negative 2, 0. Okay, and that's going to be 1, 1, and P. Okay, so that's the direction in which BD is going. So now, to write down the vector equation of this, I can say, well, any general point on the line BD is going to be equal to a point that it passes through. Well, I know that it passes through 5, negative 2, 0, plus a multiple, and I'm going to use mu this time instead of lambda, so mu times by, and this is the direction that it's going in, 1, 1p. Okay, right, so so that's the first part of this, in terms of we now know what the equation of the line BD is. I now need to solve these simultaneously to work out what the value of P is going to be. So I'm going to write this here. So in order to solve them simultaneously, I'm going to say that this bit here is going to be equal to this bit here, but I'm going to write them as single vectors. So I'm going to say, well, 3 plus lambda and 1 take away lambda and negative 6 is going to be equal to, and 5 plus mu, negative 2 plus mu, and mu times p. Okay, right, so So that means that 3 plus lambda, so I'm just going to create some more room over here. Okay, so I'm going to say that this is equal to this, so my x components 5 plus mu, and I also know that 1 take away lambda is going to be equal to negative 2 plus mu. Okay, I'm first of all going to use these two equations to work out what lambda is and what mu is. Now you might spot that if I add these two equations together, then my lambda will eliminate. So 3 plus 1 is 4, and lambda, take away lambda is 0 lambda, so I'm going to have 4 is equal to, and add those together, I've got 3 plus 2 mu, which means that mu is going to be equal to a half. Okay, I could sub this back in now, and I'll stick it into this one here. So I've got 3 plus lambda is going to be equal to 5 plus a half, which is, we'll write it as 11 over 2. Okay, and I'm going to take away 3 from both sides, so that's going to tell me that lambda is going to be equal to 5 over 2. Right, so I also know, and in fact I didn't need to work that out, I've just realised, I also know that negative 6 is going to be equal to mu times p, and we know that mu is a half. So we're going to have negative 6 is equal to a half of p, which tells me that p is going to be equal to minus 12. Okay, right, so so that's our value of p found, and we found it to be negative 12. I'm just going to tidy up this a little bit, just to create a little bit more room. Okay, so moving on to part C, part 2 of part C. Okay, so we want to show that ABCD is a rhombus, and we want to state the length of each of its sides. So if I just show that we've got some points, we've got A, B, and C, and D, and if I just label those up, so call that one A, that one B, and that one D, and what we're trying to show is that AB, that this here makes a rhombus. Okay, so in order for it to be a rhombus, that what would need to happen is that the lengths of all these need to be equal to each other. So all of the vectors that connect these together, the magnitude of those vectors all need to be the same as each other. So what we're saying is that I need to know the magnitude of AB. So I'm first of all going to find what the vector AB is. So that's going to be, and that's point B, that's point A, so that's going to be 2, minus 3, and 6. So the magnitude of AB is going to be equal to, well, it's going to be the square root of 2 squared, which is 4, we'll write it down, plus 3 squared, which is 9, plus 36, and that's going to be the square root of 49, which is 7. Okay, so Okay, we've got AB, now we want BC, and we worked out BC earlier over here, so that's the vector BC, which is 3, negative 2, 6. And so that's the magnitude of BC is going to be equal to the square root of, and that's going to be 9 plus 4 plus 36, and you might notice that that's also going to be 7. And then for CD, and that's going to be equal to, we'll do D subtract C, so we worked out D over, well, D is going to be 1, 1, it's not, I beg your pardon, sorry, D is going to be 6, negative 1, 12, I'll just write that over here, so 6, negative 1, and sorry, negative 12. Okay, so CD is going to be position vector of D take away position vector of C, so that's going to be negative 12 take away negative 6, which is negative 6. Got negative 1 take away negative 4, which is 3, and then we've got 6 take away 8, which gives us negative 2. And again, we will see that the magnitude of, sorry, that should have said magnitude, the magnitude of CD is going to be equal to the square root of 36 plus 9 plus 4, which again is equal to 7. And then finally we've got DA or AD, doesn't matter which direction, I'll do AD, and that's going to be equal to, and it's going to be D take away A this time, so that's going to be 6 take away 3, which is 3, negative 1 take away 1, which is negative 2, and negative 12 take away negative 6, which is negative 6, and that's going to be the magnitude of that, and I'm sure that you've already spotted that it's going to be the square root of 9 plus 4 plus 36, which again is equal to 7. So what we've shown is that the lengths of each of the side is 7, so that means that this must be a rhombus. So as the lengths of each side are the same, therefore a rhombus. And oops. And there you go. So that's the whole question there. I hope you found that useful. I hope you found that useful, and there's quite a lot of work in there. So hopefully you've followed it as we've gone along. And I will see you again soon. Take care.